very much for the introduction. Thank you for having me. And yeah, thank you to the audience for attending. IMS Chips is a new member of the EPIC consortium, and we were asked to use this opportunity to introduce ourselves to the community, in particular our photonics fabrication platforms, and how the quantum industry can benefit from our manufacturing capabilities. So I hope this works. That looks good. The Institut für Mikroelektronik Stuttgart, or better known by our brand name IMS Chips, is a research institute and semiconductor foundry located in southern Germany, in Stuttgart. We have a 1,200 square meter clean room, and we are engaged both in scientific research as well as development and small-scale production of high-tech CMOS products for academic and industry partners. Our activities are bundled into these business units. They are integrated circuits and systems, which particularly includes ASIC development, silicon photonics, which I will focus on today, and also MEMS technology, as well as large-scale nano patterning. This is an overview of the waveguide materials that we offer here. It's already included in the title of the presentation, so no big surprise. That's silicon on insulator, silicon nitride, and soon also lithium niobate. I guess everyone in this community knows about the diverse applications of integrated photonics itself, such as data communication and various sensing use cases. But for this meeting, I wanted to particularly also highlight the opportunities of each platform for quantum applications. The biggest factors determining the applicability of each material are the transparency window, refractive index, and therefore level of integration density, available nonlinearities, as well as phase shifting options facilitated by the material. The workhorse of classical integrated photonics has in many regards been silicon on insulator, which is transparent in infrared and allows very tight mode confinement and also very high integration density. This also means that it's possible to integrate a lot of functionality into fairly short waveguides, which partly offsets the comparably large waveguide loss of single mode waveguides. But managing the loss is obviously a major concern, particularly for many quantum applications. Also, there isn't really a way to implement phase shifters in silicon waveguides, which operate at gigahertz speeds and are low loss. Nevertheless, this platform is also investigated for quite some quantum applications, such as photonic quantum computing or quantum key distribution. If your application runs on visible light or you need high optical powers, then silicon nitride is an alternative waveguide platform that we can offer to you, which is somewhat popular, especially for biomedical applications and also in the quantum community. Especially for quantum sensing applications where we rely on these waveguides essentially for routing visible light to where we need it, this is a fantastic platform. However, it's mostly passive, since the only available phase shifter technologies relies on thermal phase shifting at very high heating powers, which means that this is often used for interposers and not so much for standalone. Since essentially all available waveguide technologies so far have some significant shortcomings, especially when it comes to quantum, we've partnered with industry and other research institutions to set up an integrated photonics line based on thin film lithium niobate on insulator. This material is pretty much the king of quantum, owing to its intrinsic electro-optic effect, which enables extremely fast and low-loss switching, the strong Chi2 nonlinearity, and ultimately the possibility of rare earth atom doping for implementing quantum memory, quantum repeaters, or even integrated lasers. What we can do with these materials for you is largely determined by our lithography capabilities. For waveguide patterning, we mostly rely on variable-shaped electron beam writing, which combines the resolution and accuracy of electron beam lithography and the design flexibility of a direct writing approach with the speed and throughput necessary for full wafer fabrication. For all further fabrication steps, we mostly use I-line optical lithography, and we can choose between two laser direct writers and a stepper lithography tool for that. You can tell we capitalize on direct writing as much as possible, and the reason for that is that we focus more on early stage development and prototyping, where partners and customers don't need one chip many times on many wafers, but rather one wafer with many different chips. By bypassing mask-based lithography wherever we can, we enable our customers to perform practical testing of many different designs at a reasonable price tag. In fact, for the money that you have to spend for a spot on a multi-project wafer at a competitor, you almost get an entire wafer for yourself at IMS chips. Particularly for the silicon on insulator and silicon nitride platforms, we operate on a dedicated wafer per customer basis, and this allows us to provide you with maximum technology freedom. For waveguide patterning, which we call front end of line fabrication, you can choose between any combination of full and partial etches at a lateral minimum feature size of typically 7100 nanometers. This enables, for example, complex apatized grating structures, as depicted here on the top left, or for example, fancy combinations of strip, slot, and rib waveguides, like you can see in the top center picture. Particularly for silicon, we also offer various implantation steps, which is important for plasma dispersion phase shifters or any technology where you need electrical contact to the waveguides themselves. Now, passive waveguides are already fine for some applications, but if you need additional back-end processes, you can choose from a wide variety of options that we can offer with our technology. This encompasses, for example, one or several layers of metallization, titanium nitride heaters, selective cladding removal, suspended waveguides, isolation trenches, etched coupling facets, deep etches, backside mirrors, and so on. Here it's our philosophy to make your application possible. While we can and do rely on a wide range of stable standard processes, we're also happy to develop new processes if you need something that doesn't exist off the shelf. Another useful capability of ours is photonic throughput testing around 1550 nanometers. For purely passive test circuits, our flying probe tester runs fully automatic and delivers 800 to 1000 throughput measurements per hour at a very high reproducibility. We mostly use this for process control and device characterization. For electro-optic co-measurements, this is a little bit more manual task and much slower, but also possible. So how can you interact with us and benefit from our fabrication capabilities? The most straightforward way is to use our foundry service. As I mentioned, for the SOI and silicon nitride platforms, you can request fully custom technology stacks with full 6-inch wafer designs. For photonic packaging, we're currently developing options ourselves, but as we've already heard, there are other partners, especially in this consortium, who specialize on this specific aspect. And I would suggest that you contact them if you don't have these capabilities yourself. We currently deliver either the entire wafer or we dice them into chips. The thin film Niobate line will, however, operate on different conditions as soon as it's up and running. Here we will provide a PDK with tested building blocks to academic partners for multi-project wafers. And if you are interested in this technology for commercial applications, then you have the option to negotiate access to our line with our exclusive launch customer, which is the startup Quant. The plan is to be operational in 2026. Apart from integrated photonics, we also offer a wide portfolio of services and products, which might be of interest for this audience as well. We, for example, offer integrated photonic design and simulation services. We've also developed silicon germanium avalanche diodes, which are, however, not integrated in our waveguide platform. Particularly interesting for many photonics applications is the option to integrate the photonics chip with a driver and readout ASIC. And for this, we have experienced mixed signal ASIC designers, and we work with many foundries across the globe. One big activity of ours is to fabricate diffractive optical elements for beam shaping or computer-generated holograms for wavefront characterization, either on a chip or even on wafer scale, as well as nano imprint mastering, which is particularly exciting for mass fabricating polymer waveguides. Apart from this, we also develop and manufacture high-end solution involving MEMS processes in general. Another way to interact with us is to team up in a publicly funded research project. And this is really open to both industry and universities. These are some of the projects we've been involved with in the past or are currently working on. And you can quickly see that we focus quite heavily on utilizing integrated photonics also for quantum applications. I want to draw particularly focus on the Quantum for KMU platform in the framework of the QSense cluster, which is here at the bottom of my slide. which is targeted to German small and medium enterprises and provides access to the fabrication and characterization capabilities of the QSense partners to players who typically don't have the resources to invest in these themselves. And with that, I already want to thank you for your kind attention, and I'm open to a discussion.